When dealing with a 3000 amps 277/480 volt service and using multiple conductors in a conduit, it's crucial to understand how ampacity derating works according to the National Electrical Code, specifically section 310.15 B4. This section addresses the adjustment factors for more than 3 current carrying conductors in a raceway or cable. The question often arises whether the neutral conductor should be counted as a current carrying conductor for derating purposes. According to NEC 310.15 B4, the ampacity of each conductor must not exceed that of a single conductor in a single conduit when using multiple conductors in a conduit. However, the crucial point is whether the neutral conductor is considered a current carrying conductor for ampacity derating. The neutral conductor is generally not considered a current carrying conductor for derating purposes under specific conditions. The NEC guidelines specify when the neutral conductor must be counted as current carrying. Firstly, if the neutral conductor carries only the unbalanced current from other conductors of the same circuit, it is not considered a current carrying conductor. This is typical in balanced three-phase systems where the neutral current is minimal. Secondly, if a major portion of the load consists of nonlinear loads, the neutral conductor must be counted as a current carrying conductor. Nonlinear loads generate harmonic currents, particularly third-order harmonics, which add up in the neutral conductor. This can cause the neutral conductor to carry a significant amount of current, potentially exceeding the ampacity of the conductor if not properly considered. Thirdly, when determining the number of current carrying conductors, you should include all phase conductors and the neutral conductor if it meets the criteria mentioned above for carrying significant harmonic currents. In the scenario of using 8 sets of 4 number 500 copper conductors with 4 wires per conduit, the initial assessment without considering harmonics would exclude the neutral from the current carrying count. This is based on the assumption of a balanced load where the neutral only carries a minimal unbalanced current. However, if the building has mixed lighting, mechanical loads, and transformers for 120/208 volts loads, there's a high likelihood of nonlinear loads being present. Electronic devices, LED lighting, variable frequency drives, and other similar equipment introduce harmonic currents into the electrical system. These harmonic currents can significantly increase the current in the neutral conductor. To determine whether the neutral should be counted as current carrying, a harmonic analysis of the building's electrical load is necessary. This analysis will reveal the total harmonic distortion and the magnitude of the harmonic currents flowing in the neutral conductor. If the harmonic current in the neutral is substantial, it must be counted as a current carrying conductor for derating purposes. Let's consider a case where a harmonic analysis indicates significant third harmonic currents in the neutral. In this situation, the neutral must be counted, changing the derating calculations. In the initial setup, using 8 sets of 4 number 500 copper conductors with 4 wires per conduit, without counting the neutral, there are 3 current carrying conductors per conduit. According to NEC table 310.15 B3 A, if there are 3 current carrying conductors in a conduit, no derating is required, assuming the ambient temperature is within the standard range and no other derating factors apply. However, if the neutral is now counted as current carrying, there would be 4 current carrying conductors in each conduit. Referring to NEC table 310.15 B3, again 4 to 6 current carrying conductors require a derating factor of 80%. The ampacity of a number 500 copper conductor with a 75 degrees Celsius insulation rating is typically 380 amps, according to NEC table 310.16. Applying the 80% derating factor to the 380 amps, the adjusted ampacity becomes 304 amps per conductor. With 8 sets of these conductors, the total ampacity is 8 times 4 times 304 amps, which equals 9,728 amps. This is significantly less than the initial calculation without derating. To handle a 3000 amps service with this derating, the number of conductors or the conductor size must be increased. Using 600 kc mil copper conductors becomes a viable option. A 600 kc mil copper conductor with a 75 degrees Celsius insulation rating typically has an ampacity of 420 amps. With the 80% derating factor applied, the adjusted ampacity is 336 amps per conductor. To meet the 3000 amp service requirement, approximately 8.93 conductors are needed, calculated by dividing 3000 amps by 336 amps. This means that 10 600 kc male conductors per phase are necessary. Since conductors are installed in sets, this typically translates to more sets of smaller numbers of conductors per set. Now, consider the scenario where the inspector is requiring the use of 600 kc male conductors because the neutral is being counted. The inspector's requirement is not necessarily incorrect but depends heavily on the harmonic content of the load. The inspector might be presuming a significant harmonic load, which warrants the larger conductors to handle the additional neutral current and derating. To clarify the situation, it's important to perform a detailed load analysis, including harmonic measurements. This data can then be used to perform accurate ampacity calculations and determine the appropriate conductor size and number of sets required. In summary, the NEC provides guidelines for ampacity derating when multiple conductors are installed in a conduit. The neutral conductor's role in these calculations depends on whether it carries significant harmonic currents. If the load is balanced and harmonic currents are minimal, the neutral is not counted as a current-carrying conductor. However, if nonlinear loads introduce substantial harmonic currents, the neutral must be counted, and derating factors applied accordingly. To address the inspector's concern, a thorough load analysis should be conducted to determine the actual harmonic content and neutral current, ensuring compliance with the NEC and safe operation of the electrical system. The correct application of NEC Section 310.15 B4 is essential for ensuring the electrical system's safety and efficiency, considering both balanced and unbalanced linear and nonlinear loads. It's always prudent to consult with a qualified electrical engineer and conduct thorough load studies to ensure compliance with local electrical codes and regulations. Additional considerations should be made for ambient temperature. In NEC Table 310.15 B2 provides correction factors for ambient temperatures other than 30 degrees Celsius 86 degrees Fahrenheit. If the ambient temperature is higher, the conductor ampacity must be further derated. For example, if the ambient temperature is 40 degrees Celsius, a correction factor might be applied, reducing the ampacity even further. Conduit fill is also a factor to consider. Although not directly related to the neutral conductor, the number of conductors in a conduit affects heat dissipation. High conduit fill can increase the temperature inside the conduit, potentially requiring additional derating. Proper documentation is crucial. Maintaining detailed records of load calculations, harmonic analysis, and derating factors is essential for compliance and future reference. This documentation should be readily available for inspectors and any future modifications to the electrical system. Grounding is another critical aspect. Proper grounding ensures safety and reduces the risk of electrical shock. The grounding conductor should be sized according to NEC Table 250.122 based on the size of the ungrounded conductors. Voltage drop should also be evaluated. Excessive voltage drop can affect the performance of electrical equipment. Conductors should be sized to limit voltage drop to acceptable levels, typically no more than 3% for branch circuits and 5% for feeders. Surge protection is important to protect sensitive electronic equipment from voltage surges. Surge protective devices should be installed at the service entrance and at downstream distribution panels. Coordination studies are vital to ensure that overcurrent protective devices, such as circuit breakers and fuses, are properly coordinated. This prevents nuisance tripping and ensures that faults are cleared quickly and safely. Periodic maintenance is necessary to maintain the electrical system's reliability and safety. Regular inspections, testing, and maintenance can identify and address potential problems before they become major issues. Energy efficiency should be considered. Using energy-efficient equipment and practices can reduce energy consumption and lower operating costs. This includes using LED lighting, high-efficiency motors, and power factor correction. The NEC is updated regularly, so staying current with the latest requirements is important. Changes to the code can affect conductor sizing, derating factors, and other aspects of electrical system design and installation. Consulting with experienced electrical professionals is recommended for complex electrical projects. Electrical engineers, licensed electricians, and qualified inspectors can provide valuable expertise and ensure compliance with all applicable codes and standards. Continuous training is essential for electrical workers to stay up to date with the latest technologies and best practices. Training programs should cover topics such as electrical safety, code compliance, and energy efficiency. Communication is key. Open communication between electrical engineers, contractors, inspectors, and building owners can help prevent misunderstandings and ensure that the electrical system is designed and installed correctly. Documentation should include single-line diagrams, panel schedules, and equipment specifications. These documents provide a comprehensive overview of the electrical system and are essential for maintenance and troubleshooting. Arc flash hazard analysis is important to assess the potential for arc flash events and to implement appropriate safety measures. This includes providing personal protective equipment and training for electrical workers. Safety interlocks should be used to prevent accidental contact with energized equipment. Interlocks can be installed on doors, panels, and other access points to ensure that power is disconnected before access is allowed. Regular testing of ground fault circuit interrupters is essential to ensure that they are functioning properly. GFCIs should be tested monthly and replaced if they fail to trip. Infrared thermography can be used to detect hot spots in electrical equipment. Hot spots can indicate loose connections, overloaded circuits, or other problems that could lead to equipment failure or fire. Power quality monitoring can be used to identify and address power quality problems such as voltage sags, swells, and harmonics. Addressing power quality problems can improve the performance and reliability of electrical equipment. Load shedding systems can be used to reduce peak demand and lower energy costs. Load shedding systems automatically disconnect non-essential loads during periods of high demand. Energy management systems can be used to monitor and control energy consumption. These systems can provide valuable insights into energy usage and help identify opportunities for energy savings. Renewable energy sources, such as solar and wind, can be integrated into the electrical system to reduce reliance on fossil fuels. Integrating renewable energy sources requires careful planning and coordination to ensure compatibility and safety. Battery storage systems can be used to store energy generated from renewable sources or to provide backup power during outages. Battery storage systems can improve the reliability and resilience of the electrical system. Microgrids can be used to create self-sufficient electrical systems that can operate independently of the main grid. Microgrids can improve the reliability and resilience of the electrical system, especially in remote or critical facilities. Smart grids use advanced technologies to improve the efficiency, reliability, and security of the electrical grid. Smart grids can enable two-way communication between utilities and consumers, allowing for more efficient energy management. Electrical safety audits should be conducted regularly to identify and address potential safety hazards. Safety audits can help prevent accidents and injuries. Lockout/tagout procedures should be followed whenever working on electrical equipment. Lockout/tagout procedures ensure that power is disconnected and cannot be accidentally re-energized while work is being performed. Personal protective equipment should be worn whenever working on electrical equipment. PPE can protect against electric shock, arc flash, and other hazards. Electrical workers should be trained in first aid and CPR. Prompt medical attention can save lives in the event of an electrical accident. Emergency response plans should be in place to address electrical emergencies such as fires, explosions, and power outages. Emergency response plans should be regularly reviewed and updated. Public awareness campaigns can help educate the public about electrical safety. Public awareness campaigns can reduce the risk of electrical accidents and injuries. Collaboration between industry, government, and academia is essential to promote electrical safety and innovation. Collaboration can lead to new technologies, best practices, and policies that improve the safety and efficiency of electrical systems. International standards can help ensure that electrical equipment and systems are safe and compatible worldwide. Harmonizing electrical standards can facilitate trade and reduce the risk of accidents. Continuous improvement is essential to maintain a safe and reliable electrical system. By learning from past experiences and implementing new technologies and best practices, the electrical industry can continue to improve the safety and efficiency of electrical systems. Proper planning and design are crucial for electrical services to ensure the reliability and scalability required for future expansions or load changes. The initial design phase must include detailed load calculations to estimate the demand accurately. This will prevent overloading the system later. Consider future needs by building in extra capacity and conduit runs to accommodate future loads. This approach will make future upgrades easier and more cost-effective. Use modular design principles to make it easier to add or remove components without disrupting the entire system. This is particularly helpful for large commercial installations. Install high-quality surge protection devices at all entry points of electrical service to protect against transient voltages and surges, extending the life of sensitive electronic equipment. Employing a robust grounding system will provide a low-impedance path for fault currents, reducing the risk of electric shock and equipment damage. Regularly inspect and test the grounding system to verify its effectiveness. Implement a comprehensive preventative maintenance program including regular inspections, cleaning, and testing of equipment. Proper maintenance prevents unexpected failures and extends the lifespan of equipment. Use thermal imaging to identify hotspots in electrical panels and connections, indicating potential issues before they cause failures. Install remote monitoring systems to track key parameters such as voltage, current, and power factor. Remote monitoring enables early detection of problems and faster response times. Implement a robust cybersecurity plan to protect critical infrastructure from cyber threats that can compromise electrical systems. Secure communication protocols and access controls will help prevent unauthorized access. Use energy-efficient equipment and practices to minimize energy consumption and reduce operating costs. This also reduces the load on the electrical system, extending its lifespan. Power factor correction can improve the efficiency of the electrical system and reduce energy costs. Installing capacitors to improve power factor can significantly reduce losses and improve voltage regulation. Utilize variable frequency drives to control motor speeds and reduce energy consumption. VFD adjusts motor speeds to match the actual load requirements, resulting in significant energy savings. Implement lighting controls such as occupancy sensors and daylight harvesting to reduce energy consumption. Automated lighting controls turn off lights when they are not needed, saving energy. Use building automation systems to integrate and control various aspects of the building's electrical and mechanical systems. BAS systems optimize energy usage and improve overall system efficiency. Regularly train personnel on proper operation and maintenance procedures. Training ensures that personnel can identify and address potential problems before they escalate. Maintain up-to-date documentation of the electrical system, including single-line diagrams, panel schedules, and equipment specifications. Accurate documentation facilitates troubleshooting and maintenance. Establish clear communication protocols between all stakeholders, including building owners, operators, and maintenance personnel. Effective communication ensures that everyone is aware of any issues and can respond quickly. Perform regular power quality audits to identify and address any power quality issues that may be affecting equipment performance. Addressing power quality issues improves the reliability and lifespan of equipment. Use uninterruptible power supplies to provide backup power for critical equipment during power outages. UPS systems ensure that critical equipment continues to operate during outages, preventing data loss and downtime. Install backup generators to provide extended backup power for essential loads during prolonged outages. Backup generators ensure that critical operations can continue even during extended outages. Consider using a microgrid to provide a more resilient and reliable power supply. Microgrids can operate independently of the main grid, providing power even when the grid is down. Explore the use of renewable energy sources such as solar and wind power to supplement the electrical supply and reduce reliance on the grid. Renewable energy sources can reduce energy costs and improve environmental sustainability. Implement demand response programs to reduce peak demand and lower energy costs. Demand response programs incentivize users to reduce their energy consumption during peak demand periods. Regularly review and update the electrical system designed to ensure that it meets current and future needs. Periodic reviews ensure that the system remains efficient, reliable, and scalable. Engage with industry experts and consultants to obtain specialized knowledge and expertise. Expert guidance can help ensure that the electrical system is designed and maintained to the highest standards. The appropriate use of personal protective equipment is paramount. Always use arc-rated clothing, gloves, and face shields when working on or near energized equipment. Never bypass safety devices or procedures to save time. Safety should always be the top priority. Regularly inspect tools and equipment to ensure that they are in good working condition. Damaged or defective tools can pose a serious safety hazard. Follow all lockout/tagout procedures to ensure that equipment is de-energized before working on it. Lockout/tagout procedures prevent accidental re-energization, protecting workers from electrical shock. Use insulated tools to prevent electrical shock when working on or near energized equipment. Insulated tools provide an extra layer of protection against electrical hazard. Maintain a safe working distance from energized equipment. Maintaining a safe distance reduces the risk of arc flash and other electrical hazards. Avoid wearing jewelry or metal objects when working on or near energized equipment. Jewelry and metal objects can conduct electricity and increase the risk of electrical shock. Ensure that the work area is well lit to prevent accidents. Adequate lighting improves visibility and reduces the risk of trips and falls. Use ground fault circuit interrupters in wet or damp locations to prevent electrical shock. GFCIs quickly interrupt the flow of electricity in the event of a ground fault, protecting workers from electrical shock. Properly store and handle flammable materials to prevent fires and explosions. Flammable materials should be stored in approved containers and away from sources of ignition. Follow all safety regulations and guidelines to ensure a safe working environment. Adhering to safety regulations reduces the risk of accidents and injuries. Regularly review and update safety procedures to reflect changes in technology and best practices. Continuous improvement in safety procedures ensures that workers are protected from emerging hazards. Promote a culture of safety in the workplace. A strong safety culture encourages workers to report hazards and follow safety procedures. Provide regular safety training to all employees. Safety training ensures that employees are aware of potential hazards and know how to protect themselves. Investigate all accidents and near misses to identify the root causes and prevent future incidents. Thorough investigations prevent recurrence of similar incidents. Encourage workers to report any safety concerns without fear of reprisal. Open communication about safety concerns helps identify and address potential hazards. Recognize and reward employees who demonstrate a commitment to safety. Recognizing safety achievements reinforces the importance of safety in the workplace. By implementing these measures, the electrical system's reliability, scalability, and safety can be significantly enhanced, providing a solid foundation for current and future needs.